Okay, grade 12, we're going to be looking at the Doppler effect. So just before we get started, just a little note. This is quite a small section in your paper one. It is physics, but it is also a very nice section. It's really cool the way it works, and it's also some nice easy marks, a very small amount of theory, very, very limited maths that they can ask you to do. Yeah, basically all you need to do is be familiar with how to use the equation and know the few little points of theory involved here. Okay, so first off, the definition of the Doppler effect. It is a change in the observed frequency due to the relative motion of a source and an observer. Okay, so important notes here is that the observed frequency is changing, not the actual frequency. So you're going to have a source emitting a sound, not the actual frequency of that sound, but the frequency that an observer or a listener might hear will be different. And the reason for that is because there is going to be relative motion between the source and the observer. Okay, what that means is if, let's say you are in a car, okay, let's say you are inside a car, you are going to hear, and you push your hand on the hooter, you're going to hear the sound of that hooter at a constant frequency, at the actual frequency of the hooter, okay, even if the car is moving, because relative to the movement of the car, you're actually stationary, because you're moving with the car. But if you are outside the car, if you're standing in front of the car, and the car is approaching you with the hooter going, then you will observe a different frequency than the frequency you would hear inside the car. Okay, so I'm going to show you how that works. Oh, that's not, sorry. I'm going to show you how that works. Oh, forgot my train of thought. Okay, before we get started on seeing actual Doppler effect, I just want to show you the way that we're going to depict waves here. Okay, so Doppler effect happens with sound waves and light waves, and actually with waves, physical waves in water, in a pond, in the ocean, that sort of thing. Okay, so whatever our source of the waves is, it could be a star emitting light, it could be a source of sound, it could be a wave generating machine at Sun City or something. Okay, so whatever it is, that's the source of the waves. In grade 10, we didn't so much talk about this, but it is logical that waves do not move linearly, right? When I speak, if you just sit in front of me, you'll hear me, but people to the left and right of me will also hear me, and people above me will also hear me. Okay, so it doesn't just move in a straight line, it radiates outwards, the sound waves, or any waves. Okay, so if that's the source of our sound, then the way that I'm going to be graphically depicting waves is using concentric circles. Okay, concentric meaning they have the same center, they have the same point as their center. So try and imagine that these are perfect circles. In this case, if our source of sound is stationary and we have somebody standing over here listening to the sound, they're going to be experiencing the actual sound. They're going to hear that sound at the actual pitch that that sound is being generated at. Because we need to remember that V is equal to F lambda, right? The relative velocity between the source and the man is constant. The wavelengths are constant, or they're supposed to be. Okay, so the distances between the wavefronts are constant, which means that the frequency will be constant. This man will hear the frequency of that wave at the exact same pitch as somebody standing over here. Okay, at exactly the same pitch as somebody standing over here. But now things change when either the source is moving, the source of the sound is moving, or when the observer, the listener, is moving. Okay, so that's where the relative motion of a source and an observer come in. Now we've got two scenarios. In grade 12, we don't deal with scenario where both source and observer are moving. We deal with scenario where your source is moving but your observer is stationary, and then another scenario where your source is stationary and your observer is either approaching it or walking away from it. Okay, so keep picking up my dishcloth to clean, sorry. I'm going to break it up into the two scenarios, but I mean really it works the same way. It affects the maths slightly different, but in terms of the logic it works the same way. So we're going to look at scenario 1. On your notes I called it scenario 1 first. Okay, and in scenario 1, that is the scenario where the source moves, okay, and the listener or the observer is stationary. Okay, now I will, in a little while, show you an animation of both scenarios, but for now, just sort of try and bear with me. Imagine if we had our source, okay, and if it were moving to the right, then do you agree, as it moves, it emits those waves, okay? But because it's moving, that means the center of each wave is slightly further to the right each time. So my first wave center will be here. My second wave center will be slightly to the right because my object has moved. My third wave center will be even more to the right because my object has moved. And what that results in is that our wave fronts actually end up looking, I hope I can do this nicely, like this. Okay, where the first wave is the one that's moved all the way out, right? Its center is further to the left, it's here somewhere. And my next wave, that's that one, its center is further to the right a little bit. My next wave center is a little bit more to the right. Until eventually I'm going to keep having a scenario like this, where, okay, that was a terrible one. Okay, my source is going to keep emitting sound while it moves so that my waves actually end up, if you can see here, in the front they're bunched together and behind it they're sort of more spread out. Okay, now the way that that affects the observed frequency or the perceived frequency is that if I had a person standing exactly in line with my object, okay, if this object was passing by my person. So let's say it's a person standing next to a train track and a train is going past. If the train is in line with the person, then this person will experience the actual frequency of the source because it's experiencing the actual wavelength. Okay, so if you are in line with the source of the sound, then this guy is going to hear the actual pitch of the source. Okay, if we're talking about sound here, but this works for light as well, it works for waves as well, physical waves in water as well. So he will hear the actual source of the pitch because he experiences the actual frequency. Okay, but if I have somebody in front of my source or behind my source, things are going to be a little bit different. So if I have somebody stood over here, I'm going to do a red guy and green guy. If I have someone standing over here, okay, then the experienced frequency is going to be much higher. Remember, frequency is the number of waves that propagate per second, right? So he's experiencing a much higher frequency, that's correct, sorry, he's experiencing a much higher frequency because these waves are bunched together. So the wavelength is much shorter. If you don't want to think about it logically, you can also just look at the maths of it. So reminder, V equals F lambda. So if we want to compare wavelength to frequency, we can say frequency equals V over lambda, which means frequency is inversely proportional to wavelength, okay? Okay, so if our frequency is inversely proportional to wavelength, and if you're stood in front of a source that is approaching you, then your wavelength that you're getting is much smaller. So if it's a smaller wavelength, you're experiencing a greater frequency. So if this source were emitting sound, greater frequency means higher pitch. Okay, should have seen that in your notes from yesterday, a reminder of grade 10 wave sound and light. Okay, so this red man, he will hear a much higher pitch, not necessarily much higher, but it will be a higher pitched sound than what the source is actually producing. Okay, and the reason for this, because he perceives a higher frequency. Okay, it's not true that the frequency is higher. It's that he is perceiving a higher frequency because the waves are bunched. Okay, now this is an informal way of saying it. The waves are bunched, i.e. this is the formal way of saying it, the wavelength is shorter. Okay, and if you are ever expected to explain it more than that, that's unlikely. It will normally be a 2-mark question. They'll ask you, does he experience a higher pitch or a lower pitch? And you can say higher pitch because he's experiencing a higher frequency. The perceived frequency is higher. You can normally stop there. But if it's worth more than 2 marks, maybe go on to explain it's because the waves are bunched, i.e. the wavelength is a little bit shorter. And if it's worth 4 marks, then you can explain because of our wave speed equation, we can deduce that frequency is inversely proportional to wavelength. So if wavelength is shorter, perceived frequency will be higher, then pitch will be higher. Okay, so that's our red man. He stood in front of the wave. So the source is approaching the red man. Then if we draw ourselves a green man on this, I don't know where I'm going to write the explanation for the green man. I'm running out of space. Okay, here's our green man. I have to erase my headings, sorry. I'm going to put the green man's explanation over here. Okay, so our green man, he's standing behind the source. Okay, the source is moving away from him. So as the source moves away from him, he's experiencing a longer wavelength. And if wavelength is bigger, frequency is smaller. Smaller frequency means lower pitched sound, if this were a source of sound. Okay, we will talk about light in 2 lessons time, but we're just going to really focus on sound for now, but it works the same for light. Okay, so because he stood behind the source is moving away from him, we can say that this green guy, he will hear a lower pitch, okay, a lower pitched sound, because he perceives a lower frequency. Okay, the reason he perceives a lower frequency is because the waves are spread out. Okay, sorry, let me focus more on writing a bit neater. The waves are spread out, i.e., okay, spread out, informal way of saying it. Good for in your explanation, but you won't really get a mark for that, but it's the way you understand it. So because the waves are spread out, then we can say scientifically that means the wavelength is longer. Okay, so because our wavelength is longer, it means we've got spread out waves, therefore he's going to experience a much lower perceived frequency. Okay, it's not the actual frequency, he perceives a lower frequency, or he observes a lower frequency, and therefore he will hear a lower pitched sound if this were sound. Okay, so I'm going to pause you there. That's basically the explanation of scenario 1, where your source is moving, but your maneki is stationary. Okay, I'm going to do the second scenario. It's a little bit harder to draw it, but I'll do the second scenario where our source is stationary and our maneki is moving. Okay guys, so here is scenario 2. If we have a stationary source and a moving observer. Okay, so our source is now staying still, which is why we are back to seeing concentric circles. It's not bunched anywhere. Okay, so the waves have a constant wavelength. Okay, there's no bunching, there's no spreading out. So what we will see here is we're going to see a person moving. Now I'm going to show him in 3 different positions during his movement. Okay, so he's going to start over here on the right. Can you see down here? Sorry. Yeah, okay, so he's going to start over here on the right, and he's going to move. He's going to pass the source of sound. Okay, that's an important position there when he's passing the source of the sound, and then he's going to keep moving over to the left. Okay, so while he is approaching the sound, this is going to be very difficult to draw graphically. I think it'll make a lot more sense when I show you the animation rather. But as he is approaching the sound, okay, so here's our maneki. He is approaching the source of the sound. Okay, as he approaches the source of the sound, now you've got to try and think about this. Maybe you can think about this in terms of if you're running next to somebody, or if you're in traffic. Okay, so if you're in traffic and you are moving, he's moving to the left, right? These waves that are coming towards him, they're moving to the right. So these are moving in opposite directions, our man and our waves. So if you're in traffic and you're going okay, let's not do traffic because you're not going to be going very fast. If you're on the highway and you're going 100 kilometers an hour and a car comes past you going 100 kilometers an hour, then the difference in your velocities is massive. It seems like he's going much faster than he really is. If you compare that to if you're on the highway going 100 kilometers an hour and someone's going next to you at the same speed, then if you look out your window, they're going the same speed as you, right? There's no relative difference in your motion. It almost looks like they're stationary if you imagine that you're stationary. Does that make sense? So if you're on a highway going forwards and somebody comes past you in the opposite direction, then the relative velocity is much higher than if you were going in the same direction. Okay, so because he's moving to the left and these waves are moving to the right, they're going to be passing him quite quickly because he's moving towards them. Okay, so he's going to experience, he's right there, he's going to experience the same as the, I think he was red in the previous one as well, I don't know, the same as the guy on the right hand side in the previous scenario as well. So he will experience a higher perceived frequency, okay, for the same basic reasons. Okay, he's going to experience a high perceived frequency because the wavelength he is experiencing is shorter. And now this is not because it's bunched up, because it's not bunched up, right? The actual waves are the same everywhere. So the reason for this is because the relative velocity between him and the sound waves is very high. Between waves and listener or observer. Okay, so that is if he is approaching the source of the sound, okay? He's running towards the sound. Then as he passes the source of the sound, so he's at this position here, here he's blue, okay? Okay, let's just draw him on top of the source. Okay, so as he's here, as he's passing the source of the sound, okay, so let's, passing it or in line with it, here he's going to experience the actual frequency, okay? So this is, yeah, that's basically what I would say. He's going to experience the actual frequency of the sound. Okay, so I'm going to use some symbols here that we are going to use when we get to the maths, but for now, yeah, I'll show you again when we get to the maths, but what I'm basically saying here, he will experience the actual frequency is that FL, the frequency of the listener, the perceived frequency at this point is equal to FS, the frequency of the actual source. Okay, so at this point, the frequency of the listener, the perceived frequency, is equal to the actual frequency at the source. Okay, and then when he's run past it, so now he's past the wave, or the source of the wave, okay, so he is moving away from it, there we go, away from, here he is going to experience a lower frequency because if something is moving at a certain velocity to the right, okay, he's moving to the left, these waves that he's getting here are now also moving to the left, which means the difference in velocity between his velocity and the velocity of these waves is going to be much smaller. It's like you driving in a car going 100 kilometers per hour and overtaking someone going 80 kilometers per hour. When you overtake them, it's a slow process. Even though you're both going quite fast, relatively it looks like they're going quite slowly. It's a slow process. So because he's overtaking these wave fronts at a slower relative velocity than he was overtaking them here, because here they were going in opposite directions, now here they're going in the same direction. So when he's moving away from the source of the waves, he will experience a lower perceived frequency. Okay, because the wavelengths he's passing are longer. Lengths are longer. And it's, again, not because it's spread out, because the waves are not spread out, but it's because the relative velocity is low. But again, it's very unlikely you'll ever be expected to explain it to this degree. It's usually sufficient to just say the reason he's hearing a lower pitch is because he's moving away from the object, or because he's perceiving a lower frequency. Okay, so the relative, what was I saying? The relative velocity is low. Okay, and that is basically all the theory for the section. So I'm going to pause you and set up my laptop because it's dying on the couch, and then I will show you the animations that I wanted to show you of scenario 1 and of scenario 2. Then you can see it, especially scenario 2, you can see how he passes those wave fronts much faster when he's moving towards it compared to when he's moving away from it. Okay, so I'm going to pause you and then I'll show you the animations. Okay guys, so this first one is scenario 1 where your source is moving. So you can now see that bunching up much clearer. If you're standing in front of the source and it's approaching you, you're experiencing a much higher frequency, versus if you're standing behind it and it's moving away from you, you'll experience a much lower frequency. And low frequency means low pitch if it was sound. Okay, then the next slide is going to be for scenario 2. So here, that's the source of our sound. Okay, and if our maneki is stationary, he hears the actual sound, but as he moves towards it, you see how much quicker he's passing those wavefronts, much higher perceived frequency. When he's directly in front of it, he's experiencing the actual frequency, and as he moves away, look how slowly, okay, we'll see it again, but you must watch how slowly those wavefronts pass him as he's moving away. So as he's moving towards it, the frequency goes 1, 2, 3, 4, 5, 6, 7, 8. Okay, quick frequency or high frequency. And as he's moving away, 1, 2, 3. Okay, much slower, much lower frequency, and therefore much lower pitch. Okay, that's it. Yeah, I'm going to send you the note. There's no questions to answer. It's basically just theory for today, and then tomorrow we're going to get into the maths.